Good morning, all. Welcome to the EasyPower Tuesday webinar series. Today's the first of a two-part presentation on the requirements of the National Electrical Code as it pertains to device coordination rating and energy mitigation. My name is Jim Chastain. I'm an applications engineer here with EasyPower, a friendly elbow bump to all. The NEC makes it clear that new design and selective coordination is considered engineering level work and should be done and approved by professional engineers. An arc flash study is neither of these activities. It's a function of the arc flash study is to verify the current standing of the equipment rating and incident energy levels to determine if a correction is called for. And so that's the focus of my presentation, how to use EasyPower tools to verify the current condition of the electrical system, and then how to produce the information needed to substantiate that fact. Welcome to all, and with that little disclaimer, I'd like to start with my poll question, which is the NEC Article 110.24 requires that field marking of available fault current at service equipment locations is required. And so the question is, which of the following are true? Date of the calculation method must be on the label. AFC, the available fault current must be used to calculate the arc flash incident energy, and the available fault current be used to determine the PPE. So let's see, check all the ones that apply or that are true. So we're going to test you here just starting off. Looks like we have a pretty healthy attendance today. We do appreciate your support of EasyPower by attending these webinars. Anyone attending today will receive a certificate of attendance automatically. There's nothing else you have to do, just sign in. So it looks like we're close to a quorum here. Let's give it another 5 seconds. Sounds good. Okay, here's how people have weighed in. It looks like a pretty wide distribution of answers. It looks like the third AFC must be used to calculate arc flash incident energy. As much as I hate to admit it, this is something of a trick question because the body of Article 110.24, which is a requirement for available fault current, is that service equipment at other than dwelling units shall be legibly marked in the field with the available fault current, which, if you read the other segments of definitions, includes maximum available fault current or maximum current, and that the calculations shall be documented and available to those. The field marking shall include the date of the fault current calculation was performed and be of sufficient durability to withstand environment involved. The calculation shall be documented and available to those who design, inspect, maintain, or operate, and then refer to NFPA 70E for assistance in arc flash hazard assessment. So to be accurate, the only correct answer in my poll question was the first one, which was the date of calculation must be on the label. It is a misconception that the arc flash incident energy has to be based upon the available fault current that's on the label. And that's why they refer to the details of NFPA 70E for calculation. So apologize if I hurt anybody's feelings. Well, let's kind of get on the road here. So as I mentioned, what we'll be covering is the discussion on interrupt ratings, fully rated and series rated equipment, and how it's covered in EasyPower with specifics on fuses, breakers, and then the ability to use Scenario Manager for a worst case report on each of the buses for that rating. Then we're going to get into coordination for fuses and multi-case circuit breakers and how that's covered in EasyPower. The topic of mitigation and coordination of low voltage power circuit breakers and relays we'll cover next session. So the NEC requires protection of entire electrical distribution systems from damage due to short circuit faults, and as detailed in 110.10, the overcurrent protective devices shall be selected to permit the circuit protected devices used to clear a fault to do so without extensive damage to the electrical components of the circuit. Now there's two methods of overcurrent protective devices will clear without damage to themselves. One is to make sure they're fully rated, and the other is if you have series rating. A fully rated system is one that has all the overcurrent protective devices tested and rated at to meet or exceed the available fault current. So in this particular system, we're showing an available fault current on this main bus of 31,000 plus amps, and each of the devices that we've indicated are rated at 65,000 amps. So it's relatively easy to see, and this is detailed in the device rating from the device library. So the point to be made here is, and when I get into EasyPower, I'll show what I'm talking about. It's important to make sure as we enter the data on a particular device that we've connected that data block to the device library, because that's where this rating number comes from the manufacturer. So the fact that we've just set up the part number and we have it connected to the device library puts us at a disadvantage. The tool will allow us to kind of check on that. The series rating is a little different matter, and this involves using an upstream device to improve or buffer the downstream operations of devices that may not be as standalone fully rated to accept the fault current that they'll be exposed to. And so the bottom line is both devices will likely clear the available fault, and it's a scheme that's found on commercially competitive projects because it allows to have lower rated devices that may be from older systems to be protected by this series rating testing. Now this is important because this is not something that can be done in the field. It needs to be done by a certified lab or the manufacturer. And so usually that information is provided as far as what upstream and downstream part numbers can be utilized is found in data sheets or tables that the manufacturer can provide or will provide. Now in EasyPower, when we set up a part number in the dialog box, this is the short circuit tab that I was referring to. And if we've set up the part number in the specification tab and then have not clicked on the calculate button to change this number changing from 0 is verification that the part number has been found in the device library. And then if the manufacturer's datasheet indicates that this part can be used in a series rating scheme, it'll be certified here based upon which one we check. So let me kind of walk through this and see if we can't make sense of it. So the part numbers that for the manufacturer indicates the rating is high enough to be able to fully rated. So this is the upstream device. Once we set the part number up here, once I go to short circuit focus, I need to make sure that I clear or that I calculate, excuse me, this is not the upstream, this is the downstream device. I want to make sure it's connected to the device library. So once I've entered the part number, I click calculate. This number changing from 0 to 18 says, okay, I found the data sheet the manufacturer has, the details in the device library, and now when we go to utilize this in the circuit, it will use the TCC information to indicate whether this is going to be protecting the downstream devices. Now, if we go back to the one-line diagram and go into short circuit focus, the test for equipment duty rating is handled by Looking at current, right now I'm going to look at a half cycle, three-phase bolted fault, which is the worst case fault that can happen in a device or a system. Fault all the buses, and I can see my ratings on this bus is 25,000 amps, ratings the exposed current, which is on the oblique. Let's just be clear about that. In line from upstream, I see what the fault current is coming from, in this case, the utility to this bus. The number on the oblique indicates the total available fault current on that bus, and it will include any motor contribution that downstream loads will have during that first half cycle. Now, once I'm in this condition, which is a fault of all buses and a three-phase bolted fault, the tool makes available to me the equipment duty icon, and this does a check against a threshold level that I've set. To set the threshold level, I go to Short Circuit Options, Control, Equipment Duty Threshold, and what I've set for this particular project is a negative 10%. What that means is if I want to see anything, any device that's within 10% of its rating, and so if this number was a negative 8%, it would still be compliant, but it would be inside of this threshold. The fact that this is showing a plus 82% means it's over-dutied and clearly not being protected, or the manufacturer can't support its data sheet in this environment. Now, if we go back to my database edit and look at that data block, we can see, sure enough, it's rated for 18,000 amps, so it's going to be well over-dutied with a 25,000 or so fault. However, we consider series rating, which the tool will look for an upstream bus, an upstream device that the manufacturer has indicated has been tested. The tool will verify, okay, this interrupt rating is based on an upstream breaker labeled square D I line HG. If that is changed, then the series rating may not hold true. So once I click OK there, the data sheet indicates that this part has been tested and will survive a 35,000 amp exposure. So at that point, I can go back to my short circuit focus, look at half cycle current, fault all the buses, and now my equipment duty threshold is indicating I'm well clear of the 10%. Where does the fuse data? Well, we're going to get to the fuses here in just a second. Okay, so this is series rating specifically for breakers. Now, that's a good point. And that is, if I go back to my presentation, the selective coordination applies to a number of different articles in the National Electrical Code, and it has some commonality between them, and we're not going to get into each of these. We're going to basically cover about the overall requirements. Coordination per se is the ability to selectively isolate a fault. For instance, we have a fault on a remote load. That fault current is going to be felt by several different devices in the system. So in this case, the feeder breaker, the main breaker, and then the fused primary will see that fault current. And ideally, any of those three breakers could open or clear the fault, but there's a downside in which one is chosen, because if the fuse goes first, then we're going to lose the whole plant. If the main breaker goes first, we're going to lose several different other feeders. So ideally, the main device that we want to have fault is this localized feeder breaker. Now, the tool that's used to indicate or to verify this information is the time current characteristic curves. And each of these plots represents a different type of protective device. For instance, this gray golf club looking shape, this is a typical trip characteristic curve for a multi-case circuit breaker, and its characteristics basically reflect a thermal setting for overload and an instantaneous setting that's tripped by a magnetic device, and consequently we have a fairly large vertical band, which gives us some flexibility, but also some trouble coordinating if we're using all multi-case circuit breakers. The blue shape is a low voltage power circuit breaker, and it has adjustable settings for long time setup, short time pickup and delay. We'll talk about that more next week. And this rust color band is actually the fuse performance curve, and the thickness represents the plus or minus, if you will, acceptance rating or acceptance band that the manufacturer guarantees from the testing that's done in the factory. So selective coordination, the standard rule of thumb in fuses is to have the same type or same family have a 2-to-1 ratio at each stage to ensure coordination. Well, EasyPower coordination we use a module that we call Power Protector to do coordination, and it gives the ability to incorporate a sequence of events, check, then look at the TCC plots, and then be able to select alternative sizes from the device library. And so the point, and I've jumped over the rating here for some reason, I'll get back to it. The point that I'm making is that these are all tested by the manufacturer as far as the coordination, and as long as you stay in the same family, the 2-to-1 ratio holds fairly constant. So if we have an upstream line side fuse in an RK1 class, and so it seems like this is a little fuse, I forget where I took this, but if we have an RK1 class, little fuse, yes, and a part number, then if we stay in that same class, which is RK1, we can expect to see coordination if we maintain a 2-to-1 ratio between the fuse sizes in the 30 amp to 600 amp range. However, if we use an RK5 as the downstream fuse, we need to maintain an 8-to-1 ratio between the upstream and the downstream fuse to be able to maintain coordination. So that's what we're looking at here, is comparing these two spots. So let's see how this goes. So we get back to I'll talk about fuse rating in just a minute. For some reason, it got out of order. Okay, so here we've built from the same family several different feeders with a 2-to-1 basis. So where we have an upstream RK1 and a downstream RK1, and we can see by looking at the individual fault, half cycle, 3-phase bolted fault. And if we look at what I want to look at is coordination. Fault a single bus in coordination, we get a sequence of events indicator, and by utilizing the sequence of events icon, we see that we have coordination with this downstream fuse tripping in 15 milliseconds and the upstream fuse tripping in 55 milliseconds. Same is true for if we change from an RK1 to an RK5 downstream and fault this particular bus, we see we have a problem because the downstream trip time is 1/4 of a second and the upstream trip time is 55 milliseconds. And so the way to maintain, and so this is trying to use a 2-to-1 ratio with different families. If I use different families as indicated by the lookup table and sustain an 8-to-1 ratio, then I can see that I have coordination here between two different part types. The way I can verify that is look at the TCC curves. So if I'm in coordination and I'm looking the same family on a 2-to-1 ratio, I can see I have coordination between these two fuses because the curves never cross in the current range that we're talking about. If I look at same family, the same ratio, got to be a little quicker on the draw. If I look at the same family, different family with the same ratio, we can see the plot there indicates there is crossover, which means they're not coordinated, at least over this particular current range. And then finally, if we use a 8-to-1 ratio with different families as indicated by the manufacturer's table, we can see in the current range that we're talking about that we do have coordination because the curves don't cross. Now, the question came up, how do you determine rating of series ratings on fuses? And the answer is in EasyPower, we don't. If I have a fuse, this is as good as any. If I have a fuse in my data block, I set up the part number, I go to short circuit focus by looking up calculate or hitting calculate after entering the part number. This is the interrupt rating for this particular fuse. Now, if there is the ability to do series rating, it's something that needs to be verified by the manufacturer. And so if I have a downstream fuse, in this case, it'll still show me the 200,000 amps, but if for some reason this was lower than my rating, the EasyPower doesn't have that information in the device library. So the point I'm trying to make is if, and this isn't the case, but if for some reason this came up with 10,000 amps, and the manufacturer said that by using these two fuses in series, I could get a coverage on a series rated basis for this downstream device of 100,000, then I'd enter the 100,000 here and then not click calculate as a result. The benefit is now that this would be used in the equipment duty calculations in EasyPower, but I would want to make sure that I comment that I use the equipment duty rating from the manufacturer's data sheet if that were the case. So series rating for fuses and fuses covering breakers is not part of EasyPower's device library because it involves too many manufacturers trying to cross-connect different part types. Okay, so I think I stomped all over that one. Now, the series coordination has been updated in the form of an informational note, which includes this illustration on a number of articles that I kind of referred to earlier. And the point is to answer the debate concerning how to handle overcurrent protection devices on the normal side of a transfer switch. So the question is, if we were going to have series coordination, what applies to the normal settings on the power supply versus the emergency or standby settings by switching the ATS? And the bottom line is, when we're looking at an emergency source, then D needs to be coordinated with C, C needs to be coordinated with F, and F needs to be coordinated with E as far as each individual devices. Likewise, if I'm on the normal power, for some reason I don't have my clever little diagram that shifts my rectangle to the left, D needs to be coordinated with C, C needs to be coordinated with B and A. Bottom line is B and A don't have to be coordinated themselves because they don't have any loads in common with the emergency side. So it's a little bit of it makes sense, but it's a little bit difficult to explain without having a specific example. So anyway, this is included in the NEC, and coordination is a little bit of a pain with multi-case circuit breakers. So that's what I want to touch on next. Again, multi-case circuit breakers include both a thermal and a magnetic trip unit, and they're difficult to coordinate. So there's two ways to consider selective performance, either by limiting the time of the period of time that we're comparing the two curves, or current constraints where we can guarantee coordination at a certain point on the curve. And this information is usually published in manufacturer tables It is included in the device library, and if we were to look up in the multi-case circuit breaker particular manufacturer and pick out an upstream device, in this case a square D I-line HD, these are the downstream devices that are shown, and the conditions and the voltage and then the maximum current for which there's coordination. Now the way this looks in EasyPower is something like this. Let's kind of go into Rolando. I'll get to your comment in a second. And so what we want to do is verify that we have multi-case circuit breaker coordination in the case where we have two circuit breakers. And as I mentioned, there's multiple ways to get there. If we look at coordination, we got a single downstream bus, and look at half cycle current and fault the bus, the tool will tell us the sequence of events. And so what we see is with the fault on this bus, this lower breaker will trip at 460 milliseconds and the upper breaker at 13.7 seconds. Well, the point is we're showing half cycle current, and these trip times are well out into 30 cycles or close to 30 cycles. So if we pick that as our tripping point and fault the bus again, the times don't change, but the current does. So I need to fault the single bus. All right, so the point that I'm trying to make, and this is clarified when we look at the TCC plot. If we focus in on the trip time at this particular current, fault the current, we have tick marks determined by the settings we have on the breakers. And these settings are determined in the short circuit tab. The tick marks were showing when we set this up, we were looking at momentary current. So let's set the tick mark at 30 cycles. And let's set the tick mark on this one at 30 cycles. And at that point, we can see most definitely we have BL2 will be clearing the fault at this point, which looks like it's just under half a second. And BL1, which is the main breaker above, won't be clearing the fault until close to 15 seconds. I'm showing 12 seconds there. So we have coordination, and this is what was shown on the chart. We have coordination below 1300 amps, and indeed it's due to this. So there's a constraint on how much current we can show, because if we go into if we have fault current out in this range, we will not be coordinated. Okay, don't know that made sense. Let me see if I've messed anybody up. Yep, Naveed got it. Yeah, and Rolando explained the lateral loads better than I did, so I'm not going to try to explain that one again. Okay, so and so the point being, we got two ways to deal with coordination. One way is, and what we've done here is say, okay, below 1300 amps, these two breakers are coordinated because we definitely can see that the downstream breaker will trip first. The other way to do it is to say, okay, at any particular time, and in this case, anything over 3/10 of a second, any fault that lasts over 3/10 of a second, we know for sure that the downstream breaker trips. And so this is a technique that's utilized to, and we'll talk more about this next session, is used on emergency systems to verify we have coordinations in the case of a fault that lasts longer than a certain time frame. Okay, so basically we've talked about interrupt ratings, that are listed in Article 110 and the definitions in Article 100 for fully rated, series rated, and an EasyPower that covers fuses, breakers. I wanted to talk about Scenario Manager for the worst case. So just real quick, if we go back to, for those of you that have never done a short circuit study in EasyPower, probably one of the more valuable tools for determining the worst case fault current at every bus is available in the form of the Scenario Manager. Because once we've defined the system and then all the different, let's see if I even have an example of this. For all the different configurations of my, wouldn't you know it, I can define different configurations of the breakers showing cross-tie breakers, other sources of energy. But the bottom line is to define scenarios that include each of those configurations and then create a comparison report for equipment duty. And this will give us the ability to generate a custom report that shows either just the scenarios we want to show or all the scenarios and comparing the worst case fault current for each one. And again, in this case, because we only had the base case, but this will be the worst case fault current for each of those levels of current, showing the duty cycle that's has been calculated. So frequently, this is a very good way to show the worst case current at each bus, which is another report that's worth having, showing a client. Okay, we also talked about coordination for fuses and multi-case circuit breakers. We'll be a little bit better prepared in 2 weeks for mitigation and reducing arc flash incident energy with relays and low voltage power circuit breakers. I apologize for running a little long, but I do appreciate you attending. And if there are any questions I wasn't able to get to during the broadcast, we will follow it up by email. Thank you for attending.